Welcome back to FA3. I don't know if it's the English that is scaring people or if it's the technology that's scaring people. We're a very small group.
Or lunch.
Or lunch. In that case, it probably killed them. So we are a small group, so if you have questions, just ask them immediately, because discussion is always better than just talking. The first talk this afternoon is by Dr. Christoph Hanisch. Some of you might know him from many future or other organizations. And I leave the word to you, Christoph.
Good afternoon. My topic this afternoon is the future of evolvable, adaptable production systems from a European industrial perspective. I will talk later a little bit about technology, but my main motivation for doing work in this area is some of the arguments we had this morning. I think we need to reconsider the humans in the production environment. These are not the stupid operators that drive the clever machines, but these are the guys that are able to walk back to the parking lot in the evening and have the idea on how to improve their work the next morning. And I promise you will not find any machine on the world that can do that. And if you look at bigger technological achievements, you will find that they are driven by people that are convinced of an idea, that are convinced of values, and that will not stop thinking when they leave the door of the office in the afternoon. So our challenge to meet the global problems we are confronted with is really to evoke these values in people again. And also we heard something about this morning, what a company would like to have as an employee and how machine and man interface should work. I think the event here today is an important one because I think and I hope it will bring together industry and academia backed up by politics for a midterm perspective, midterm strategic perspective. We cannot allow fuzzing around with this goal this year and the next goal next year. We are working on systems that are to support people, to bring them a standard of living, and these machines have a long life cycle. What can you expect this afternoon? I will say some words about the company I work with or work for, where I see the starting point and what problems we have, the wind and direction as a determining factors for sailing, evolvable systems. So technology will come rather at the end, but I think you will see why we need to consider important factors in the surroundings if we want to move forward in production technology. And my conclusions at the end. I work for an independent family-owned enterprise which sets the scene, so to speak, for a different way of investing, for a different way of investing in people and of valuing people. So a family business wants to be in business still tomorrow and is not really interested in the short gain revenue. Siemens is quoted of having said, "I have not the means for the short profit. I need a longer strategy." You see some figures, 16,000 employees. We increased by 1,000 employees last year, and 350 of that in Germany, so not just in Asia. And we increased in turnover and so forth. We are trying, and I can say only we are trying to think global and act local. You cannot really divide that. And we regard ourselves as being interwoven with our customers' interests. Our customers are in the automation business for many different sectors, like automotive, food packaging, and so forth, all confronted with the question, where do you produce, how do you produce, what is your factory like, where do you get your return of investment from? So, welcome to Festo. Why is your event, in my view, so important? I think we need research for production. Many people think of production as an old art. You make your hands dirty. It's not even state of the art. But we need to understand the function of the research in that area. And we need to understand that if we want to advance, we need scientific interdisciplinary answers for production and production systems. And we need to understand the importance of local production. We have lost and destroyed many lives by outsourcing, and I will come back to this later. We are in a very interesting period of time because the Western societies need to recognize and are starting to recognize that we cannot live by the short cost labor in other countries, because they say, look, we are people as well, and we want to live as well. As a baseline of this, we need to grasp manufacturing as a discipline. It is not just a conglomerate of many different engineering sciences, but it is a discipline in itself, and therefore the Express Lab is a very important activity as I see it. And we have to water this plant. We have to think about it, we have to understand it, and we have to care for it and not destroy it every other year by a new strategy. Historically speaking, we've been confronted with the evolvable and the adaptable way of producing with an assembly net exercise about 10 years ago. Many companies that are active in the area of assembly and automation got together to write a coordinated action paper for the European Commission, saying what would you think of how assembly should look like. And it is not important that you can read the details of that. It is only meant you see integration on both sides, and it is integration of processes and methods, of technology, adaptable technology. What do you need to do for technology to achieve systems that can be adapting to new situations in a very short time? And you see a time scale 2002 to 2010. In 2011, January 2011, last year, we were the first time able to really prove a mechatronic agent, which is a mechatronic unit that is run by a decentral control and that can negotiate its processes with its surroundings. If you go back to Festo, our strategy has been dominated by the triangle in the middle. We are producing components for automation, which means we need intelligence components on a very low level. So we need small actuators, we need actuators including sensors, we need low energy drives for that purpose and so forth. But we need to build on the second level mechatronic systems that include control and that are more than the single component. And for a long time, we just said, okay, we need to do this because our customers are the ones that produce the systems, so our components should fit into the systems. This is why you have systems at the very top level. It was quite a time later that we recognized we need to talk there of production systems, especially of adaptive production systems that can be the future. And I say can, it will not be the answer for all problems. On the left side, you see a little darker services. It took some time to understand that in a pneumatic or electric pneumatic automation system, you have already a lot of information which you can use for condition monitoring, process optimization and so forth, which means we as a company have to understand our components as part of a system and to be used in a system. So the driving force behind what we did in our research, where I work for, is determined by these three levels. And of course, the two lower levels are the most important ones for our business, but we need to see where it focuses for in the future. At the time we came across these questions, it was the hype time of MEMS technology, which means microelectronic devices, building on microelectronic technology, possibly including physical actuators and so forth, devices that by their very nature cannot be assembled by hand. So what happened is you come up with a product design, and the product with the perfect technology, because it's small enough, it may not be cheap enough, but it's at least small enough, but it is for sure not producible, because it does not make sense to produce such small volumes with a high-end automation line. To give you an example of that problem, we produced with a partner a foil that is reacting to the pressure. So depending on the air pressure, it changes the color. So it would be a perfect pressure indicator for many places in our lines. But we would need 1 square meter of that foil for years' production of sensors. And you will never find a chemical company that produces just 1 square meter for you. So this brought really home the question, how can we design our components to make them more adaptable and to reshape the production systems of the future? Sorry, I went the wrong way. And this is where we came across Manufuture. And Manufuture, a long time ago, said we need to change from cost cutting to value adding. It is a change in mind. You find in many places that, of course, production just has to cut its costs and you will produce and sell your products happily. We have reached the bottom line of that. We cannot produce cheaper in China anymore. We need to go to Vietnam and maybe move out to the Pacific in the year afterwards. So this mechanism doesn't work anymore. At the time when we introduced this paradigm, many people laughed at us. This has changed. We need to think on processes that are value adding. And you see on the right side, it includes high performance, but it also includes new human capital to create the value for the people that work in these processes. And this is a provocation to technology in a way, because you need to design technology to fulfill these needs. So we came to manufacturing as a research innovation-based activity, not just an engineering skill for making the electric device faster, quicker, less energy consuming. What is our problem? Our problem is very simple. When we talk of things that we have to produce automatically, we have to design lines that do that or machines that do that. And the typical situation for this automation is shown in this diagram. 1/2 of the costs are management, mechanical parts, and the control parts. These are basically fixed. So you can get a better deal for your mechanical components, or you can find a supplier that does the welding for a little less. But basically 50% of your equipment costs are fixed. You can move around locally a bit, but this is fixed. The big part is on the left side. This is where the ramp up and the installation happens. The writing of the software, debugging of the software. Someone changes the machinery and you have to go step by step through your process and adjust your software so that after 6 months you have a stable running process. If we are able to design machinery that helps us to cut this by half, for instance, then we have done really a big step. And the interesting part, this is what I mentioned at the beginning, for me is that I think we are at the level of technology where this is thinkable and realizable. It's still a long way to go because software coding and so forth and tools to design and make them industrially safe is a long way. But we have reached the control power capacity that will enable us to do that. If you look around, what do we have? We have many technologies and technological solutions that are interesting. We have tested simulation, we can design that technology, we have calculation methods that allow us to predict many features of this technology. We have complex manufacturing technology, we have advanced material, and we have even virtual reality, so we can design a product. If you look at our valves, they are rather small. We can simulate the flow through these valves and illustrate that in virtual reality. So we have a room where the engineers meet and look at the air current through these valves. There is no way of former methods to illustrate calculation results in that depth. So you look at this 3D virtual reality and you see air particles coming in, rushing by certain corners with supersonic sound, and they we need to adjust the curvature. There is no way of testing, no way of sample building in speeding up this process and optimizing design. So we have very powerful tools, and we also have the belief we only need to have further on the best technology. And this is what others prove wrong. We have gone through this when you mentioned this morning Asian are looking different at this. I know a well-known German car company that has lived by that standard. We just need the next step of better technology to keep the best car in the world. And they find that the technology has to be embedded in human processes that allow for further optimization. If you look at Toyota has worked on that for over a period of 10-15 years now, and they have a lead factory in Japan. In Japan, they don't give the technology outside that has improved productivity by 40%. And this is not done by technology alone. It is by dedication of people, by convincing people that it is really necessary to work on themselves, to seek new ways of doing things and putting that to practice. And there is where technology meets the humans. Speaking about Japan, Professor Yoshikawa is, at least has been for a long time, the driving force behind the Advanced Industrial Science and Technology Institute in close to Tokyo. He realized early that it is not sufficient to talk about research as research. You need one step back. If you connect that to industrial processes, there is, of course, research that is basic research and that will be necessary without any question. But there is research that is dedicated to solving industrial processes. And there, it is not just possible to talk of a single effect, not just of a nice laser that has more power or is quicker or a smaller focus. It has to be embedded in the industrial processes, and they run through several waves of problems. At first, you have basic research type 1, where the discovery happens. You will amount to problems before the night period starts. And in the night period, most researchers are gone because they have published their papers and they are not involved in the industrial processes that need to be implemented. And this is not a criticism on research. It is a necessity to understand the two roles both have and how they have to cooperate to solve that. Professor Yoshikawa gave also a very interesting and illustrative example. His question, how to fry an egg. On research level, we are very easily to say we have to optimize the material of the pen, or we have to study the time behavior of the heating process, or we have to study the energy consumption of the heating process. But this does not fry the egg. Frying the egg is getting the egg somewhere. You need to know where and in what quality. You need to know how to handle the egg. And you need to carry the egg to the place where you fry it. You have to take it out of the pan. So the process of frying an egg is a very provocative question, because in many cases we are thinking about the pen material, and many of our German politicians at least will say, oh, we have the innovation how to fry an egg, but they are missing completely the boat. If we understand the ingredients of this question, we can make Express more successful and a very important tool. Others are not sleeping. Here you see action plan for Japan's manufacturing industry from the MITI, the Japanese ministry. And you will see, if you read it a little bit, it is not improving the lather or building a new production system. It is about upgrade the domestic competitive environment, measures to increase profitability through improvements to job cooperation, to Japan's corporations' excessive competitiveness. It is about caring of emergent markets in the rest of the world. And they have very, very tight procedures of measuring that. And they will work on that for 10 years, and then they will be successful. Compare that with our way of cooperation between industry and research and politics. And even America, which destroyed lots of its manufacturing industry, has woken up. So there you see that President Obama in June 2011 brought a big program into reality. This is where people start to understand the real level of problem we are in, and that we cannot solve it just by this or that nice research project. If you are setting sails for the Express Lab as you do today, you need to consider the wind and decide on the direction. The wind will determine where you can go and what is possible, and the direction you need to decide where to go. And I will make some remarks on the wind first. The wind are the weather conditions, in parentheses, under which industry in Europe is operating. And we are writing the year 2012. So the word remaining risk, a risk of 10 to the minus 23 or 30, is not sufficient anymore. You've seen that in Japan with Fuchikura. Raising costs of transportation is an open secret, so you cannot just outsource it to place X and Y and Z anymore. You really have to think on how to produce in locally. On the upper right you see small holes, and these small holes almost destroyed European industry. These are the fans of an engine, a jet engine of an aeroplane, and these holes have a diameter of a few hundreds of millimeters. And when we had the Iceland volcano erupt, we had glass particles in the air, and these holes are necessary for keeping the air, for cooling the turbine to a temperature that it does not melt down. So once these holes are blocked by the glass particles, the plane will just crash. It is an image and a reminder that we have to deal with hazards which just not leave us to move around as if we are free to do anything. We are confronted with raising labor costs in many parts of the world. ABB had a study last year comparing electrical engineers in Europe and in Asia and in Brazil, and the factor between those was in labor costs was 1 to 2 to 1 to 3, so not factor of 10. And the interesting part is that it raised over the last 2 years tremendously, closing the gap. And we are recognizing sustainability as an issue. This is the last picture on the left side. which is determining our survival, so to speak. We have learned to deal with ecology since the 80s. So we are reducing waste, we are nice about paper and separation, the other waste and so forth. We are understanding that it is an economy issue, so we have developed businesses that live on sustainable issues like solar energy and things like that. So it is not just a request to spend more money. The social science, that these enterprises have to care for the social sustainability of the people involved, is just at the verge today. So our understanding of manufacturing is starting to change slowly. We are recognizing the importance, the controlled importance of production more. It is not old technology, it's nothing you need not to worry about and everyone can do. But it is a complicated discipline that needs interdisciplinary scientific answers. So many of the problems in the production are not be solved hands-on. Well, hands-on, we discussed this a little different this morning, but it is not easy to solve them. And we need to do this if we want to keep our standard of living. Where are we heading? We are heading toward the end. Are we learning? Are these learning machines being the controllers of our production sites in the future? Is this fantasy? Is this vision? Or is it a necessity? Where do we want to be as engineers in the future? Is the factory an entity out in the green? You put in the drawings and the material and the products fall off the belt and are delivered via internet in the end? Is the engineer then the guy that goes out fishing? And where do we want the other 95% of the populations to be? Do we need to lock them away because they don't have anything to live on? In any case, if you look at the story of the egg, technology as such is not the one that will solve the problem. Technology is embedded in human systems and has to be dealt with as such. Nevertheless, and this is where I come to my fascination with technology, I learned from Thijs Reinders, so there's a guy in the middle, is a colleague from Philips, who made the example of digital photography where we are used to have analogous pictures and where we now with a digital means can produce a digital picture of a physical reality and manipulate that reality in our computer. In the production environment, we can do the same. We have reached the control power to have the physical reality of our processes of whatever linked to images in the computer one-to-one. This is the important thing, one-to-one. So what we do in the virtual can be downloaded to the physical immediately. So we have the possibility to write the control program in the virtual, download it, and the machine will run as a computer-imitated picture in the first place. This leads to our dream of evolvability, and we will talk about this later today. Fractals is a mathematical way of imaging sets that are, no matter how much you magnify the details, always similar. So if you can have a production line where you just plug in a new device, like an USB stick, the machine knows its device is new, it has a position, it can do this and this and this, and it will negotiate its process with the rest of the assembly. And this will have real-world implications. So I'm not talking about out of the sky. ABB Flex Framer is a machinery with robots that assemble car bodies. And these robots could, of course, be decentral controlled and have additional features as they had in the past. We gave a proof of concept some time ago in a European project called UPAS by building up a physical line. If you look close enough, you would see that we built many Potemkin villages, so it's still lying about certain things, but it opened the way to agent decentral controlled assembly devices. It leads the way to the real factory being adaptive in real time. So the image between the physical and the virtual being linked so intrinsically that whatever you do in one or the other realm, or whatever happens in one or the other realm, can be downloaded to the real world immediately. This will open new management procedures, and it links to your presentation in a way this morning. We need software to follow process, and not the other way around. We spend lots of money in our companies on software that fulfills part of the job, that kills other processes too early, and so forth. There, we meet the IT world often in the way that they seem to know where we need to go, but don't understand our processes. Small example, you see here lines. The black veins are modules, assembly modules linked to a transport belt. And we came up in the Ideas project with a very simple, and we've done many, many discussions and work on that, for an agent control assembly system where you plug in a machine and it will be decentral controlled and negotiate the process with the product and how to produce it. Make it a little more illustrative. The starting point for Festo are components. As you can see him there, you see a valve terminal on the upper part and different pneumatic or electric devices that are used for automation. With a new way of thinking, we will bring these modules together with their own control, all being equipped with an agent, and then the agent network will run the process and the machinery. The change of to combine modules with decentralized controls will increase reusability. It will make exchange easy. It will take less time for the physical building and reduction of a ramp-up time, and it will reduce of the complexity in the line, in the sense that you have to care for the modules, the naming of their input-output, and not worry that you have a 30-meter line where you mistook a naming of a sensor at the end of the line and the machinery breaks down once in a while, unpredictably. In conclusion, I would like to say, with the work on evolvable and adaptable production systems, we have come several steps closer to the following points. We have new options for building automation equipment. We have an equipment to support human operators in a new form. And for me, this is really the most important aspect, because if we only work on technology, we can transport that technology to any place in the world like this, put it on the plane, shift it away. But if you link the knowledge of the workers with the factory staff, whatever you name it, with the technology, and understand that only this combination makes the optimum, and this is what the Japanese companies are beginning to understand and are really defending, then you get a big step ahead in production. It will address low and medium volume, and you might say, I could have said that in the beginning and end my talk and talk more about technology, but the technology is a function that has to fulfill a certain purpose. And if we don't understand the weather around, the weather conditions dictated by the bank situation, the weather situation dictated by the situation in northern Africa, where Europe relied for a long time on cheap natural resources without any double thinking, we will not make a good production equipment of the future. With this, I thank you for the attention, and I'm close to the time limit. Thank you.
Do you have any questions for Christoph?
I have just one comment or question. You were talking about virtual reality and modeling everything, and you're sitting there behind the screen and you think you can do everything, but the model has to be correct then. I'm thinking of this airflow example you were talking about. How do you verify that the things that you really do follows your model in practice? How do you connect your models to the real world?
Let us build it step by step. So you have calculation methods for mechanical analysis, for nonlinear mechanical analysis, for electromagnetic analysis, for rheological, so filling a tool in plastic injection molding. For all these tools that are professionally programs you buy, you need a time of, say, 5 to 8 years to understand what you have to do to be 5% accurate. So it's not just buying the tool and being happy and you can calculate. No, you need to calculate and measure. And in our case, we have a testing department that tests our components on life endurance many times. Failures are discussed, analyzed by metallurgical methods. So we know there the difference when we come close to that, and we can rely on the theoretical prediction in a way that we do not need to build a new sample before we can go the way. The same is true for the virtual reality. In the sense, of course, you cannot go into the small component and see it by your eyes or make it visible in any form. There is a method with polarized light where you can build models, scaled models, and you can see the flow and you can compare the flow of the scaled model to what you calculate. You have a direct link to your flow calculation when you optimize the sound of you have devices to cut down the sound. I'm not sure on the English word. It's a damping mechanism, and you can measure how much of the original noise compared to the new methods. And this is air flowing through very many small pores. And from indicators like this, you know that you're on the safe side. And you can measure the air consumption, for instance, in your switching procedure. And if you have parts where you have supersonic velocity of the, you will hear this in the outside in your valve, and you will see when you have the new model, that it is improved. So I cannot say, yes, we've seen the real, but I can say, yes, we have a method of discussing on how to improve, and this works well enough to be in alliance with our other testing procedures. Okay?
How do you connect your models to the real world?
Let us build it step by step. So you have calculation methods for mechanical analysis, for nonlinear mechanical analysis, for electromagnetic analysis, for rheological, so filling a tool in plastic injection molding. For all these tools that are professionally programs you buy, you need a time of, say, 5 to 8 years to understand what you have to do to be 5% accurate. So it's not just buying the tool and being happy and you can calculate. No, you need to calculate and measure. And in our case, we have a testing department that tests our components on life endurance many times. Failures are discussed, analyzed by metallurgical methods. So we know there the difference when we come close to that, and we can rely on the theoretical prediction in a way that we do not need to build a new sample before we can go the way. The same is true for the virtual reality. In the sense, of course, you cannot go into the small component and see it by your eyes or make it visible in any form. There is a method with polarized light where you can build models, scaled models, and you can see the flow and you can compare the flow of the scaled model to what you calculate. You have a direct link to your flow calculation when you optimize the sound of you have devices to cut down the sound, I'm not sure on the English word. It's a damping mechanism, and you can measure how much of the original noise compared to the new methods. And this is air flowing through very, very many small pores. And from indicators like this, you know that you're on the safe side. And you can measure the air consumption, for instance, in your switching procedure. And if you have parts where you have supersonic velocity of the, you will hear this in the outside in your valve, and you will see when you have the new model, that it is improved. So I cannot say, yes, we've seen the real, but I can say, yes, we have a method of discussing on how to improve, and this works well enough to be in alliance with our other testing procedures. Okay?
Okay.
Okay.
Thanks, Christoph. Okay, as I told you, Professor Bharata is not able to be with us today. So I had a look at his presentation, and I think it actually fits better if I take that one first. And you will understand why as I go through it. Professor Bharata is a friend of mine. We have known each other since 2000. And in fact, everything he presents in this presentation, I have been a part of with him. So I can follow his line of thought fairly well. And ideally here is Express and how Express can benefit from European projects. And I think I'm going to bring you through the history of how FA3 at least came to be what it is in Express. Now I said earlier Express sets its objectives from many European road mapping efforts. And in fact we started back in 2000, in fact. And I think Christoph mentioned it, the Assembly Net thematic network. This was a very large forum in the fourth framework of the European Commission. You can see how many partners they had. There was quite a lot of industry, both large industry and SMEs. And we had about 4 years upon us to answer some questions. And the loss of products through outsourcing is obvious. What became obvious to many companies in Europe is that although they were obliged to outsource, they were losing process knowledge. And process knowledge is a core competence. Now, many products are built or assembled manually. When you outsource from Sweden to a low-wage country, who are the first people to lose the job? The operators. They have the process knowledge of your product, and you are losing it automatically. As soon as you outsource and you fire the operators, the intricate knowledge of your process is lost by firing the operators. And this is especially difficult for SMEs because they cannot invest in automation as it is today. So with the excuse of mini and micro assembly, which was the trend at the moment in early 2000s, we decided to look at this, and we had all the partners possible, partners that developed the technologies, business partners, producers, vendors, and academia. And we really spent 4 years looking at this. And what would be the needs of European industry? and how could we create new research projects to support what was needed, especially by SMEs. And in fact, the AssemblyNet roadmap came out in 2003, before the ManuFuture roadmap and before many other roadmaps in Europe. And what we saw was that there was a huge market segment available to Europe, but we didn't know really how to get it. So basically, we went around Europe asking many questions to companies, like, for example, should we maintain assembly competence in-house or should we outsource? And almost always the large majority would say that the core competence of assembly should be kept in-house. It's not that they were outsourcing willingly, they had to for cost reasons or for market reasons. So this was detrimental to them, but they couldn't do anything about it. What type of assembly they were outsourcing? They were really trying to outsource sub-assemblies that were not core technology. Very successful companies outsource only the final assembly. The really secret company, important assembly was still being done in-house at a heavy cost. And to whom are we outsourcing and why? And this, I think we all know the answer now. It's low-wage nations, emerging markets, and we're doing it to cut cost. It's not even market presence. It was really about cutting costs. A lot of people, especially economists, will say, you have to outsource to be near the market. It's not true. The world isn't that big. You can do it here in Europe and still ship it there. And if you have an economic crisis, which is huge, like in 2008, the advantage is you don't have a lot of half-made products halfway to China. Because that's another backside of outsourcing. If you have a big recession, and you're producing somewhere else, you have unfinished products somewhere around the world. So really it's cost. And this is it. And it comes from the industrialists in Europe. We really need to go to low-cost, reusable automation. Now, Christoph said sustainable. That is the big word. It's a trendy word. It has so many aspects to it that I don't even want to consider it. It's economic sustainability, ecological sustainability, technological sustainability. We can be here for 3 days and we'll still not find out what it is. But we have to make it cost effective. So the equipment can be reused and it doesn't cost an SME a fortune. And this is the roadmap Christoph showed you a while ago. This is what we developed. The date for when we believed we could achieve evolvable or adaptable production system is 2012. Okay, if we did everything according to plan, we would have an adaptable production system running by 2012. When AssemblyNet finished, the partners got together and created a lot of European projects. So it led automatically to a lot of ideas. I have only some of them here, not all of them. The one that became very important to us was UPAS, because it really picked up on the idea of evolvable or adaptable production systems and tried to achieve them in reality. And this was a big project. The budget was of 21 million euro, financed by the Commission. So the partners came in with just as much, about as much. 21 partners, and the coordination started with Philips, and then Philips jumped out halfway and we took over the last part. So very, very large project, very, very ambitious. And I will come to the conclusions of UPAS on a while, but we were also interested in UPAS to find out about what Christoph calls the weather. Okay? What are the conditions around us that will determine the technology that will succeed in the future? Because you can create very, very good technology, but then something might happen, like oil will finish or silicon will run out and everything goes up the, down the drain. So we have to look at all the conditions. And very, very briefly, I will show you some of this. For example, demographics. I mean, Europe is a continent which is shrinking. It's not even growing. The other continents will double in their population. And Europe is becoming smaller in relation to them. So by 2100, we will only be 7% of the global population. And that makes you think. Globalization. This is a message to the politicians. If we are going to outsource, if we are going to help companies invest in R&D, can we make it feasible or interesting for them? I mean, in many countries, if a company puts some of its gains into research, it's tax deductible. In Europe, you can outsource high-tech research, and nobody says anything. It should be controlled. And there's many, many aspects here that have to be looked into, especially because manufacturing is about 75% of European revenue, okay? And if we lose it, we're dead. And it's not the big corporations that we're talking about here. It's the SMEs that make the backbone of Europe, okay? So politicians have to take this very, very seriously, is that there has to be legislation that helps investment in R&D. If we look at the venture capital, you can definitely see the effect of the 1990s recession. Sweden was hit quite early, probably 94. It really had an impact of how companies were investing in R&D. The problem is that Europe is always lagging behind the United States. And it's getting worse. Because whereas once upon a time we were investing in research at a much higher rate than emerging nations, some emerging nations are now investing more than Europe. So if we believe, like Christoph said, that we can continue outsourcing to these emerging nations, forget it. There is no nation that is investing more into robotics and high-tech production than China at the moment. So that is something that should wake everybody up. So automation needs will increase, okay? And I'm sorry, Lena. Our kids are not making enough kids. I did what I could, but it wasn't enough. So we are going into a negative trend. And EU regulation has to account for the fact that manufacturing generates almost all of our benefits in Europe. It's our standard of living. Tourism won't be enough. Ecology, aging populations, nanotech will create new markets. It's true. There will be new markets, new products. It will be interesting for us, but it's not enough. And one thing that came also surprisingly from an American study is that our management has to become much more technologically oriented. If we go back to the 1960s, and look at the Swedish companies that became globally known, Electrolux, Atlas Copco, Ericsson, they were all created by engineers and run by engineers. They are not anymore. They are run by economists, businessmen, who don't have really touch with technology. The companies that succeed in the long term always have technology in the leadership. It's no surprise that about 70% of the Chinese Politburo consists of people with an engineering degree. Okay? Try to find that in Europe. So management really needs to become more technology-oriented because we cannot think in the short term like we have anymore. With this, in 2009, UPass actually went on and created a new project, the Ideas one, and it actually started out of the Express FA3 initiative called Instantly Deployable Evolvable Assembly Systems, and it started at the same time as Express about. So there was a continuation from AssemblyNet to UPass and to Ideas. Once again, it was a European project, not as large, 7.9 million euro, EC financing around 4 million euro, and we are coordinating it. The project is running now. It's halfway, and I will talk about it in the next speech. This is why I thought it was better to bring this one first. But why mention this project? Because in November 2011, the IDEAS project actually demonstrated an evolvable assembly system at Festo in Esslingen. And this system could configure itself, and it was multi-agent based, completely decentralized control. Every module had its own controller. Nobody needed to program it. And according to the roadmap I showed you before, we were supposed to achieve that by 2012. So we actually achieved it 1 month before schedule. Okay? So it is quite interesting that roadmaps will work if you put them in the right context and there is capital for research behind it. Okay? And this is what happened. The European Commission actually fulfilled some kind of obligation here. It didn't just leave the results of AssemblyNet away and changed and said, oh, we'll do some work on sustainability now. No, they sponsored UPAS, they sponsored ideas, and after 10 years we got there. And this is what we have to get through to even Swedish financiers. It's no good if the research agenda changes every 3 to 6 years, because it takes at least 10 years to make technology viable. So European projects are really essential because they will allow you for multi-sectorial collaboration. And what Christoph is saying is true. Future production systems are not only the domain of production engineers, computer engineers, biologists, businessmen, everybody have to collaborate. You cannot live in a little world anymore. And it allows for realistic risk-taking in R&D. There is the capital available to take some risks. I don't really find the same in Sweden, I'm afraid. I have been applying for the same type of project in Sweden since 2004. I didn't get one financed in Sweden. They think it's high-tech or science fiction. We are looking at the next generation after evolvable assembly systems. Evolvable is old for us. So that's the kind of scale. We have to be careful. And when I say that, yes, I hear too much lean, I hear too much DFA, things, yes, they are old. These things were discovered in 1987, 1988. We cannot be working with them now. The Japanese are working on completely different things at the moment, and we're not even mentioning them. So we have to have risk-taking in R&D. Another thing about European projects is that it has created long-lasting links with industry. The link with Festo is one of them. We have links with a lot of companies in Europe, and they have been invaluable to us, bringing us with our feet back to the ground, telling us what is possible and not possible from an industrial perspective. Finally, European projects will give you critical mass. You need a lot of partners sometime to achieve a goal. You cannot have small projects. Sometimes you need big projects to get somewhere. And finally, I would say that going out to Europe as an academic person, I found out that the demands are higher. You have to really be world best to be out there. Okay? So it kind of sharpens the level of work you're doing. So European projects will continue to be essential for us, even in Express, and especially because FA3 is multi-sectorial. We have product design, we have human aspects, metrology. We really have to find this multidisciplinary approach. And in fact, although IDEAS project is still running, and I will present it in 5 minutes, we have actually sent a new proposal now, which is called My System, and it's looking at exactly what Christoph was saying. Now we have adaptable production systems. We know how to build them. We have to make them industrially viable, but we know in which direction to go. But what demands will that put on all the people involved, from the people who create the modules to those who work with them and the businessmen and everything? So this project is going to work primarily with the automobile sector, and I think that is an indicator. How come the automotive sector is interested in a project like this? is a clear indication that even complex products like cars want to be in as many variants as possible. So it was also no surprise that Christoph showed the ABB Flex Framer, because an assembly line has thousands of robots today, and you would like to change 3 or 4 on the run without reprogramming. So European projects will continue to be vital. I wish sometimes that the level of research would be raised in Sweden as well. I'm being provocative here, but I would really like to see some more basic research in Sweden at Swedish level as well. I think we owe it to our companies. Finally, why is this important? And this is a philosophical change. I told you earlier, I don't believe in flexibility anymore. Flexibility is about doing a lot of different things fairly well. That's doing absolutely nothing fantastically well. Okay? So you're basically buying a system that has functionality that you don't even know when you're going to use it. But we're used to that. We're used to creating systems that we can plan every link and that we have to see where each link goes to in the next step. And it permeates our society. Our military think in exactly the same way. If we're going to attack a country, and we saw this in Libya, it took 2 weeks to get an air cover working. Okay, 2 weeks to just get the airplanes to fly over a country, because everything is so tightly coupled. And this is how we're building production systems. Everything is so tightly coupled, everything has to be sure before we do anything. And we lose every time because these guys set it and go out in 5 minutes. Okay? And I think you're going to laugh, and after a while you're going to think that this is really serious, because they will win. We have to change our philosophy from extremely tightly coupled systems where we think we can predict every next step to a solution where we say, I'm going to need this then, and I just have to put it in and not think about it. Okay? The technology allows it. We have our laptops that allow it all the time. We haven't applied it to industry. That's the difference. Okay? So if I want a laptop and I want to change my graphics card, I can do it. If I want to go from Windows 7 to Linux, I can do it. I have thousands of agents running in the background without me knowing it. So the technology is here. We just have to learn it. And I really believe that what we have to go to instead of flexible systems is solutions where we have very dedicated modules that can be put together very quickly and inexpensively. And I will try to present this in the next presentation. So everything becomes an organism, and we have to be able to influence one or the other and know exactly how they're influencing each other. So for the short term, I would say that adaptable systems remain our goal, but it's really how to make them industrially viable. At the same time, we're thinking about the next generation. So for us, adaptable evolvable systems are not science fiction. We have proven that they can be made, and now we have to go to the industrial application of them. Thank you. And I'm not Jose. Thank you. Okay. We're fairly in time, aren't we?
Yes.
Another 15? Only 15?
For your question.
Okay, we'll take a break then. Come back in 5 minutes. Because I'm going to be very technological afterwards. Oj, detta. Nu får ni reda på det. Med video i slutet. Okay. If we start now, we'll probably end earlier, so you're going to have a long coffee break before the next phase. What I was going to talk to you about now is the Ideas project. We're going to go into some details of it, and I'll show you a brief video at the end. Ideas is still running, and it is the project that has actually realized the first evolvable system. If you don't believe me, you can ask Christoph at the back. It's at his premises in Germany. Ideas is a small to medium-sized project. It's not that many partners. These partners were selected out of the UPass project, which was much bigger, because we all had the same objectives. And from the common objectives, we created the Ideas project. And really, it was about trying to build a system, an assembly system, that works in industry. So we wanted to go away from the academic thinking and really do something practical. So it's an agent-based approach. We have no centralized controller. We have no PLCs. This is multi-agent distributed control. Every piece of equipment has its own controller. And the thing that has been missing for these type of applications is a controller board, which is made for agent control. Okay? So what you have for industrial use is PLCs, but there's no specific controller board for agent use. And this was one of the things that we have developed in Ideas. We have an open architecture. We can use any type of platform, and the thing that turned out to be very, very intensive is the design tools, the tools that will help us create such systems, configure them, and so forth. But as Christoph was saying, what we are simulating in the computer in Ideas today, we can download immediately to the equipment. So it's a one-to-one relation. Once we simulate and we see that it works, we download it to the equipment. And this is being proven to work. What is left to do in Ideas, and which will happen in the next year and a half, is that we're going to build 2 industrial systems, one here at KTH and one in Italy, for 2 different products. The one here is going to be for Electrolux Italy products, washing machine products, and the one in Italy will be for Iveco, the electronic control boxes for light vans. So key concepts are 3 really: a mechatronic agent, and this is when you combine software with hardware, okay? And that this agent is actually capable of some very low-level reasoning by itself. It can have cognitive actions. It can adapt to a certain level to the changing environment. Evolvability is the centerpiece. We can self-organize. These systems self-organize. We don't have to pre-program, and I will show you a video about that. And by either adapting to the conditions or by changing modules, the system continuously adapts or evolves to the changing conditions. Now, because the modules are interchangeable, you don't have to buy them. You can just rent them or lease them. They can be reused in other processes. Emergence is something that we have to be very careful of. When autonomous entities collaborate and your properties come together with mine, the sum is not only what you can and I can, there will be new functionalities, okay? And these new functionalities that are born out of our collaboration might be positive, but they might be very negative as well. So we have to be careful about that. When these autonomous entities come together and organize themselves, there might be some unwanted performance out of them. So we have tried to keep this architecture as simple as possible, because in assembly, as we know, there is a lot of different needs, a lot of different processes, but we want the architecture to be very simple so that we can define as many different applications in as simple a way as possible. And we have 4 types of agents, basically. That's a machine resource agent. This is typically your robot or a feeder or a conveyor. Coalition leader agent is the agent that groups a number of agents to perform a specific process. So it might be the robot with a gripper and a feeder to do a pick and place operation. We have the transportation system agent, and this is different from a resource because transportation has to index its location, which a resource doesn't really have to do. And then we have the agent to machine interface. This is very important because many equipment today are not made for this type of control. So we have to create a kind of a wrapper, a piece of software that allows you to use your old ABB robot in this system. And that's this special agent, the AMI agent. So we can use any piece of equipment on the market today because we can interface it with the AMI. And mechatronic agents are basically the combination of a controller, which is very specific for agent technology, putting it onto your piece of equipment, which is a robot or a feeder, and then embedding into this controller the very special software, which is the agent technology, okay? Now, agent technology is very specific because it works on the basis of behaviors, okay? It will look at the behavior of the robot. It will not look at the events it has to complete. So it's quite different to the PLC type of programming where we're just following events. These kind of equipment is much more independent. They will look at the behavior and what the goal is. So they will achieve the goal and look at the behavior. And in this way, we have a whole library of equipment, and we know that all these pieces of equipment have their own controller. They are represented by agents, and in this way we can create complex systems with just these 4 agents. Here you see the coalition leader agent, which is one type, controlling 3 resource agents or 4, and in some cases you will have a coalition leader agent even controlling a smaller coalition leader agent. So you can put these things together like Lego, basically. And you're starting to see that one of the difficulties here is creating the structure of the system in a correct way that it will do what you want it to do. So configuring the system is different to what we're used to. And we are going to evaluate our systems. We have parameters, changeability. So can the system modify its characteristics? How much is it going to cost us? How much time is it going to take to change its characteristics? How much is the cost of this? Do we have to change any hardware, software? How much did it cost us? Programming. We're going to look at the effect on the product. If the system is really cheaper to run, it will influence the product. Can we start analyzing how much, if possible? And adaptability. Can the production system adapt to market changes, product changes, or just environmental changes, okay? So we're going to try to look at 3 different scenarios. Production changes are simple, like volume going up and down. Product changes are a little bit more difficult. Okay, we're going to start with just introducing a variant, but if the product changes in one of its components, then we have to change a process as well. And then the human aspects, of course. So these are the evaluating parameters which we are going to start looking into to see how successful we are. But the whole thing, the whole of the ideas concept, or the whole of the evolvable assembly system concept is based around the module. And module is a word that everybody uses, but often in a very wrong way. Module has to be a basic building block, and it has to have a standardized interface. And for us, a module represents a specific process needed by the product. So if it's gluing the screen on a mobile phone, that is a process. And this will be represented by a module, an equipment. So the product is quite easily mapped by the processes it needs, and then we know what modules are needed to build that product. The actual tasks the module will perform physically on the system, we call them skills, okay? And this is something I want to come back to again. This is a particular way of defining it because of the computer technology that we are applying here. The module has a set functionality. The module is dedicated. These modules are not flexible. They are dedicated. What is flexible is the way we put them into the system and take them out of the system. In fact, they're not flexible. They're adaptable. It's very quick to just put a module in or pull it out. But the module itself, it is dedicated to a process and nothing else. To build these systems, you need quite a lot of tools in the background. So it's no different to our laptop. When we use our laptop, it's very easy. Our kids can use it, no problem. In fact, they're better than us. But the people who build these have to have quite a lot of tools to configure them. And it's pretty much the same thing. So when we start looking at these things, start defining the processes that are needed by the product and translating the process needs into actual functionalities or skills, we need languages that interpret this so that any production engineer can do it. So these languages are being defined at the moment. They are UML based, nothing revolutionary here. We're trying to follow standards as much as possible. There is OMAC compatibility as well being taken care of. And step by step, we're implementing it now, even in automation ML, which is a big initiative in Germany at the moment. It's a UML-based type of approach for defining workflows for production systems. So there's a lot of development here, specific languages and tools based on conventional and commercially available software. So we're modifying tools to our needs. Once again, you see here the idea of skills. These are the functionalities that the modules have to have, and they come directly from the product processes. So this has to be very easily mapped by a non-expert. And finally, you have to start putting your system together, and this needs very special user interfaces, visualization tools, as they're called in this project. We have developed 2 or 3 variants and tried to test them on different levels of user, from expert user to a normal operator. So this is still being fine-tuned at the moment. But at the end, it will come out. It will be the next slide. What has been done, tested, and is working at the moment is from a software called Visual Components. We have developed a simple module where you can simulate the agents, i.e. the agent software can be simulated in this environment, and you can watch your module perform. In fact, you can have the real one next to you and just download the software and it will do exactly the same. So we have a one-to-one relation here. What you are doing on the Visual Component software will be downloaded onto the real machine and it will do exactly the same. This has been tested and it actually works. And what is missing, or what was really, really missing, and what was missing from the very beginning, one of the reasons why distributed control is not gaining any territory in industry, it's because there is no controller board, okay? You have the agent software, you have the integration tools, but what is this software going to run on? They cannot run on PLCs. PLCs are not designed to run that kind of software. So this is where the company called Eldrest came in. They are a commercial controller company, and they took one of their products, a Combo 211, and they redefined it, they redesigned it to run decentralized control with multi-agent technology. It still has Ethernet TP/IP, and at the moment we're running about 30 or 40 of them at different locations. We have some here at KTH, the ones in Germany at Festo, which are actually running on the system, and we're still testing them because there's a lot of things that have to be done on this controller. I mean, it has to run Windows C6, and you have to implement a Java virtual machine onto it. This is the machine that actually runs the multi-agent software. And this, in turn, has to have a development framework so that you know when you have the code, you can download it to the controller, etc. We're now looking at possibly implementing Linux-based on these controllers, but it's quite expensive. And really, the whole point of the exercise is to make these controllers very, very cheap. At present, I think, I don't remember, Christoph Elris, what is the price of one of these controllers, or the target price? 10 to 20 euros for one of these controllers, yeah. So it's quite cheap. You can take your old ABB robot, spend about 20 euro, program it, and it's a distributed control unit. And this is from Elris, so you can buy it off the shelf now. This was crucial. This was definitely one of the missing links. Because we have these controllers now, we can do this. And Masmec, our partners in Italy, are implementing this according to the OMAC standard so that it can be applied by any system developer. And they have their own configurator tool, which is a product which is now being fitted with all the tools I told you about before so that it can become a commercial application, very visual, very interactive. Just to give you an idea of the kind of implications this technology has. You can do the hardware, but the software implies that a lot of things need to be done in the background. At present, we can take any equipment, I said, and that's true. We can really take any equipment. We have this agent-machine interface which can be programmed. So we can run Profibus, Ethernet, anything really. We can wrap an agent around any of the present-day technology and use it within a distributed control system. This has been proven. It's fully effective. So legacy equipment is not an issue. Adaptive control, I would like to spend a little moment here because I saw that they were using this word wrongly somewhere else today. Self-learning systems. Adaptive control can be interpreted as self-learning. It is not. Please be careful. Adaptive control is conventional control of a machine whereby the machine checks some of its parameters and compensates and changes its behavior according to the error noted. This is not self-learning. We have some kind of adaptive control in our machines as well, but it's not extensive because as the machine itself has adaptability, which is really the next level, the agent knows what it's doing wrong and can change its behavior. We don't have to put too much effort on this. We are looking at self-learning. That is, how can the machine learn what it's done in the last 3 years and improve its performance? But this is a lot more complicated, and we're not there today. We won't be there in 3 years' time. So be careful when people talk about self-learning. This is really very serious and very difficult. We have self-configuration. We have almost some kind of self-organization, but self-learning is really the future. So some adaptive. The interesting thing is what happened in November, because after all the years of promising people and people telling me, oh yes, but it's science fiction what you're doing, it doesn't really exist. These things won't happen. Well, we made them happen. We made them happen in Germany at Festo with a system that was initially built for DNA analyses, if I'm correct. Consists of about 3-4 modules. The interesting thing about this piece of equipment is that the pallets move freely on a board, so there's no fixed routing. Very special type of motion of the pallets. And the task was to prove the idea on this system. So each module that you saw earlier, if I find the pointer, there it is. So each one of these got its own combo controller with an agent inside. So they were all agentified, including the funny routing which these fixtures can take. So when the fixtures move, they have to check that only one is moving at a time so that they don't collide. And it was run in November 2011. The first time, no, the first time was actually earlier. We ran it again in November 2011 for the European Commission. And I will show you this brief video. It's not the best because I had to do it from my mobile phone. And we can see that the system starts working. It mounts a pallet on the fixture. And the fixture will run along and get the first operation done on this module. Now, after this operation, there should be a module here doing a second operation on this product, but it's missing. The module is not there. It's been taken away. And what happens is that it stops because the agent says the behavior is go to module 2, but module 2 is not there, so it just waits. It waits until this gentleman plugs it in. So he just puts it in and puts the connector in. And now it's on. You will see that it takes quite a long time now to figure out what to do, and that's because they are negotiating. This module has come into the system and says, hey, I'm module number 2. Oh, really, what are you doing? I'm supposed to do this process. Okay, the fixture pallet is there. It's really you? Yeah, it's really me. Okay, then do it. So at the moment, we have restrictions here. It's taking a lot of time for us to do this because the controller is not that efficient. Okay, it takes some time to run the software on it. But there it is. It goes along and it does it. This seems nothing to people who don't know anything about production. But what you have seen is the first time ever that a system was configured automatically by itself. And this we can do time and time again now. So we can pull out a module and put it in without reprogramming, and the system knows what to do. So the basic concept of adaptable or evolvable systems has been proven. We now have to bring it the next step to a really industrial level, okay, where it's real robots in a real environment with real demands, where the volumes change every minute, where things go wrong every minute. But the concept works. And many of the things we wanted to prove and that people keep thinking are science fiction, like working society of mechatronic agents, this is a long way in the future. Multi-agent system architecture, this is only science fiction. All of these things have actually been proven to work now. So we have a little society of 5 agents. We've shown that this works. The multi-agent architecture controlled the mini-prod, and everything else according to this. So really, the message I'm trying to say is that when we talk about adaptable, evolvable systems, people say, this is the future. And I'm saying, no, it's the past. We have to go to the next generation. Industry has to apply this, okay? But we researchers have to go to the next generation. And it is in this direction, but high-tech is where we're supposed to be doing work. Now, having said that, there are disadvantages with multi-agent systems. Traditionally, there is no current agent platforms, but this was solved. We have the controller now that can run the agent technology, and it's a commercial company, and they will develop it. So we've solved this problem. Scalability problems. Can we really control very, very small pieces of equipment? The answer is yes. We have a solution to that. Development costs, we haven't solved, okay? This will come in time if the technology is matured and if people want to use this technology. But it is important to point out that many of the disadvantages of multi-agent technology have been solved now. So we can go towards the next generation. If you want to read about this, there's a lot of publications. So just contact me. But there's a lot of material published. In fact, this project is now being considered as being one of the FP7 success stories. We shall see if it succeeds in being it, but it's one of the ones selected for being a success story. If you have questions, please shoot. Yes, Ali.
Professor, you mentioned about self-learning systems. For such a system, should we go into like artificial intelligence systems and this topic, or because I just want to know if
What's artificial intelligence? I will not answer that question that way. Self-learning will obviously be some kind of artificial intelligence, but we will do it based on the multi-agent paradigm as well, with multi-agent systems. I cannot answer that question really, because we're investigating which might be the best way to go at the moment, in a very, very simple way. So the answer is not really givable at present. This is why I'm saying be very, very careful with self-learning. It's a trendy word, people like to use it, but we're a long way away from self-learning. And this is, if we do not couple human beings to the production system, we will not have self-learning. We have nowhere to start without them. The human beings have to be in the loop to begin with. And through the operators, then we can start finding the way to learn in the best possible way. That's where we are really at the moment. Yes?
Wouldn't it be the first step in self-learning? I understand, I realize that you're right, that artificial intelligence is a very, very trendy word, but let's say that you have a robot that is standing there and doing the same thing every day. Would it be possible to close loops, let's say, with sensors, so this robot itself know and can measure its own behavior? That is the first step, by just using pure statistics.
Yes.
Would that be a way forward to so the robot doesn't wear out so
Yes.
fast?
Yes.
You know what I mean?
Yes. This is adaptation. This is adaptation, and we can apply it today. Okay. So this, I don't call this learning. I call this adaptation.
Okay.
So
But
you
in the control community, it's called learning control. If you learn over cycles of the robot, I mean,
yeah.
not over years if you will.
Yeah.
But I think it's more a matter of what you learn. I mean,
Yes.
so if you want to learn from more complex situations, involving other pieces of equipment, for example, or coordination of equipment, then I agree with you. Then self-learning is much more complex.
There will be, I'm fairly sure to say that different technologies will be used for different types of learning. There is case-based learning, which is close to what you're saying. You will look at the performance of the robot in many different cases, and you will register its performance for these cases, and you register it, it can be brought back and reused. So this is case-based learning. Then you will have inference engines and these kind of neural networks and AI for more advanced applications. So really depending what type of learning, you will probably use different technologies. But it's very difficult to say at the moment. I don't have a problem with learning control. That's definitely still the right word. I react a little bit when I see the word self-learning, because that we're far away from. Yes. Thank you for coming.